Dear students, third year of Mechanical Engineering Department. Today we will discuss about multi-degrees of freedom systems. This is the first lectures of this topic. We have already come across 1 and 2 degrees of freedom till now, where simple mathematical models of complex physical systems were represented. These models were explained the dynamic behavior of the system in a well manner. Often such idealizations are not possible, and mathematical models with larger number of degrees of freedom is necessary to be considered. Here, most vibrational systems faced in physical situations have distributed properties. For instance, mass and stiffness. Such systems are said to possess an infinite number of degrees of freedom because the system is fully described only when the motion is known at every point of the system. In number of cases, the mass and stiffness distributions are highly non-uniform. For such system, more feasible to construct discrete mathematical models which require number of parameters to describe the motion and the stiffness. The motion of such discrete models are described with finite number of coordinates. In this manner, systems with infinite number of degrees of freedom is reduced with finite number of degrees of freedom. Here figure shown, this figure, that is the figure of non-uniform shaft. Figure of non-uniform shaft. Figure A. It has been converted. This continuous model is converted into discrete method. Figure A shows a non-uniform shaft, torsional stiffness Gjx, and mass moment of inertia Ix. Ggx and Ix. Ggs and Ix. Where Ix per unit length at any arbitrary point x. Figure B can be represented by discrete model or approximated by the discrete model. Approximated by the discrete model of non-uniform shaft. The motion of multi-degrees of freedom system is commonly described by the finite number of simultaneous equations. The solution of such set of equations are tedious task because of coupling terms are involved in each and every equation. So the coupling terms are removed to make equations independent to get the solutions easily. Hence, some of the methods are discussed to study the dynamic behavior of the systems. The method that is first method, that is the matrix method. Take an example. So that we can understand the methods very well. There is the 3 degree of system M. Independent coordinates x1, x2 and x3. We can take each and every stiffness, that is K. Take the free body diagram. Kx2 minus x1, second one, that is the same. Kx3 minus x2 M. So this is the free body diagram. of the above system, we can write equations for this. Inertia for mx1 double dot plus kx1 minus kx2 is equal to 0. First equation. Second equation is considering this. We can write m2 x2 or mx2 double dot plus 2kx2 minus kx1 minus kx3 is equal to 0. Second equation. And third equations we can write mx3 double dot plus kx3 minus kx2 is equal to 0. So these equations can be written from this free body diagram, and inertia terms are there, so we write it. So these equations can be put in the form of matrix, and we will get in matrix form. What we will get in matrix form? M 0 0 M 0 M 0 0 0. Here we can put in this form x1 double dot x2 double dot x3 double dot plus we can write equations clearly. K minus k 0 minus k 2k minus k 0 minus k that equation is we can write here x1 x2 and x3, and that is equal to, so this is the equations you have seen. From the equations it is kept in the matrix form. M diagonal matrix is there, x1 double dot x2 x3 dot k minus k 0 minus k 2k minus k 0 minus k, and it is in this form, and that can be equal to 0 0 0. So here the matrix is for the above systems is given. The matrix for the above system is given. Now we can write the above matrix in this form. M x double dot plus k x is equal to 0. This M is known as mass matrix. Mass matrix is small m, diagonal terms are there, m, and this is the stiffness matrix. So this M is known as mass matrix. Multiplying by M inverse both sides, we will get M inverse M x double dot plus M inverse k x is equal to 0. So we have seen this. So we can put, firstly we will put the equation number first, second, third, or we can put in this form first, second, third, and this one is matrix is 4, fourth, and this one is fifth. This one is fifth equation. So you have seen already. For understanding the matrix methods, we have considered one of the example. We are solving these examples and we understand it. Here we can also write, if you want, m1 x1 double dot, that is the inertia term, m2 x2 double dot, and m x3 double dot. Sorry, here m2 is equal to m. So you can write it. Okay, so that is mx1 double dot, mx2 double dot, mx3 double dot. So from this we can, from this FBD, this free body diagram, we can get three equations, and it is 1 2 3, and it is kept in the matrix form. That is fourth equation. So now here you have in fifth equation it clears to people that M inverse M is identity matrix, so that can be written x double dot plus a matrix x is equal to 0. This is sixth equations, where a matrix is dynamic matrix, or is equal to, you can write M inverse K. Because of harmonic motions, at x is equal to where you know very well what is x, x1 x2 x3, that can be written is equal to x1 x2 x3 sine omega t, because of harmonic motions, and that can be kept in this form also, x, where x time for x1 x2 x3 sine omega t. If you will find x double dot, what we will get? Here we will get omega square x sine omega t. This is just sine omega t. Let omega square is equal to lambda, so we can write x double dot is equal to minus lambda capital X amplitude vibrations sine omega t. So from here it clears. Putting these values in sixth equation, we will get minus lambda. We can put in the diagonal terms is there, identity matrix x plus x is equal to 0. The values of x and x double dot from equation 7 in equation 6. We got this one. So from here we can solve it. So what we can write? We can write in such a form. We can write lambda I amplitude x, okay, x is equal to 0, or determinant of this, that gives the lambda I minus a, that gives the, from here we can get the characteristics equations, and we can find the values of lambda. Here dynamic matrix should be solved first. A is equal to M inverse K Firstly, we will find out M inverse, that inverse of the matrix you are able to find out adjacent M to the determinant M. So we will get the M inverse 1 by M square 0 0 0 1 by M square 0 0 0 1 by M square. Or we can write 1 by M is equal to identity matrix 1 0 1, sorry, 1 0 0 0 1 0 0 0 1. So now we are able to find out M inverse, able to find out M inverse K, putting the strictness matrix, multiply it, we will get K by M minus K by M 0 minus K by M 2K by M minus K by M 0 minus K by M K by M. We got the dynamic matrix now. Now we know that determinant of this lambda and I a determinant of this, that is equal to 0, and then we get the determinant, we get lambda minus K by M 0 K by M lambda minus 2K by M K by M 0 K by M lambda minus K by M is equal to 0. Upon solving this determinant, we get the values of lambda is equal to 0, where omega 1 lambda 1 is equal to 0, omega 2 is equal to lambda 2 is equal to lambda root K by M, omega 3 is equal to lambda 3 is equal to lambda root 3K by M. So the matrix method is used to find out the natural frequencies of the said system. So there are three masses, so there are three natural frequencies. So based on these natural frequencies, we are able to find out the mode shapes of the system. So putting frequencies over here, x1 x2 x1 x2 amplitude vibration, x1 x2 x3 can be calculated for different natural frequencies, for all three natural frequencies. So there are three natural frequencies, so there are three set of modes of vibrations or natural modes of vibrations. So thank you.